Thanks, everyone. Today I will talk about high-performance interconnections for the integrated edge cloud and also HPC application. This project is associated with LF Edge, Acarino. We call it Type 5, IEC, Integrated Edge Cloud. My name is Funi. Yeah, I received a doctor degree, so I put doctor there. Yeah, I'm the CTO of the Clussys. Clussys means class system. So this is our website, and welcome. We are a startup to doing this, and welcome people to work together to promote the high performance interconnection for edge and the cloud. So today's topic, I will cover three parts. First one, I will just discuss the edge computing trends and what Acarino Type 5 we want to do. Second, we will introduce the interconnections technology in cloud and what is the problem and what we want to do. At last, we will show some applications. What is object storage for the like a green, like a low power consumption storage, and also we are working on the high performance storage for the HPC. Here is first one. Let's talk about let's discuss about the data flow from cloud to the deep edge. Actually, in my idea that we classified what is cloud, what is edge, based on the size of the servers. Normally, in the modern data center, we use the like a spine and leaf or Tor switch to form a data fabric. And we connect all the servers, like computing servers, GPU servers, and storage servers to the fabric. And if we think about the like a central data center or the regional data center, normally we have like hundreds or thousands, even like a million like servers to connect together. Of course, we need a scale up and like a scale out switch system or data fabric. But if we look at the edge, when we go to the like center office edge or like even the deep into the building, the campus, actually we see that most of enterprise, we only have several servers, less than 100. So, for my company, even we are doing like chip design and like high performance computing, but actually in our office, we only have like 10 to 20 servers. In this scenario, we only need several switches. Most of it are only like 2 or 3, and less than 10. So in this scenario, we need to rethink what is the scaling means, especially for the edge cloud. We put the scaling like okay, how many servers for our computing power, like G-flops, like TOPS. And then we need to design how many switches we need, like with switch amount. And then based on the switch amount, we will design what kind of data fabric we want. So that's what we call the data fabric. So we in Acarino Type 5, we think about that not like the massive cloud. We do not take the switches into account. In IEC, we need to think about the data fabric very carefully, especially for like servers less than 32. Why 32? Because 32 is a good number. So we want to have some very efficient data fabric to connect 32 servers to make the edge cloud more efficient, more high performance, but also very cost effective and green and scalable. So in the IEC architecture, we actually originally in the release 1 to release 5, we introduced the DPU. We used like a data processing unit. We use the DPU as a unified management to manage the edge cloud. In the release 6 and release 7, we introduced another like ultra low latency, like cost effective, like PCIe and Ethernet fabric. We want to extend the DPU to connect more multi-host. And that's what we said. Since the DPU is a PCIe compatible device, right, we can introduce further combine the DPU and the PCIe networking together to enable the scalability to few servers. In R6, release 6, we introduced a PCIe fabric layer to connect like 32 servers together. So we introduced a new PCIe fabric into the edge cloud. So we call this kind of like trends is the scale in, not like a scale out in the cloud. We need to scale in the edge because we just want a more cost-effective cluster, not use like a port density or like a link type. So after we talk about the trends, let's talk about what kind of link, what kind of networking we can use in the cloud and also in the edge. So the problem that in the modern data center, the first problem actually is about the cost and also about the power. If you look at very detail about the cost and in the modern data center switch, we found that the switch ASIC is very expensive, and it's very expensive in terms of the cost and also the power. And it takes about like 50% of the total power print for the data fabric. And also the optics. That's not a good idea. That's not good trends for like modern data center, especially for the green. So actually this is for the cost and for the power. Another thing is about performance. In the right side, this graph, it shows that what is the performance looks like. This graph actually comes from some, I don't know, yeah, the website. Normally people talk about the networking. Networking means like a fiber channel, Ethernet, and IB. They are very scalable. And they can scale to like thousands, even like 10,000 of servers. However, the performance and the latency is about like 10 to 100 microseconds. However, the local bus, like PCIe or CTL in future, they are about like 10 times like better than the networking. However, there are two things we need to do. First one is we need to increase the scalability of the local bus. Second one, of course, we need to improve the performance. What I say that, okay, for the improve the performance is led by the PCI SIG. This is a standard. We need to we need the PCI generation like 2, 3, 4, 5 to increase the speed, also lower the latency. But there are a lot of room to how to extend the PCIe to the multi-server, like increase the scalability. So this is the category about interconnection technology used the actually from the in the box to the out box. We call box in and out. So normally people talk about like in the box, we call the bus. For the bus, we have 3 types of connections. First one, CPU to CPU. Second one, CPU to the device, and then device to device. And then actually for the outer box, I categorize as three as well: device to device, load to load, and cloud to cloud. Originally, actually, all this outer box networking we called is a TCP/IP kingdom. People use the TCP/IP for many times. However, in the box, a lot of things happened. Traditionally, we use like Intel, like UPI, AMD, like HT, and CPU to device we call PCIe. The device to device, normally we use the PCIe P2P. However, the NVIDIA did something very different. They have the SLI originally to connect 2 GPUs, and then they evolve into like an NVLink. So we can think about that. NVIDIA actually needs to change. They use NVLink to do the device-to-device connection in the box. And also they use NVLink to do the device-to-device connection out of the box. So as we can see that today, for the super chip, like a GH200, they use NVLink to connect the GPU across the servers. So they just make the boundary between the outer box and the inbox like a blur. You cannot define what is really a server right now. NVIDIA say, okay, everything linked by the NVLink is just the one GPU. So they just want to cross the boundary. And also they introduced the NVLink C2C to connect the CPU with the GPU, like the Grace and the Hopper. And then they use the RDMA to do the NVMe over fiber to do the load-to-load. So you can see a lot of things changing today, not just in the box, but also out of the box. So we need to redefine what is bus and what is the networking. Then what the community is doing right now? Community actually doing community are doing the 3 things to counterpart the NVIDIA's trends. First one is the UCIe. They want to unify the CPU to CPU link. And then also they want to see CXL to make the device to device and the CPU to device better. And also recently they have the ultra fast Ethernet to make for the load to load connection make it better. Then there is a gap. That's what we want to do. We want to promote like some protocol to bridge the ultra-fast Ethernet and also the 6L. Of course, right now we use the PCIe because PCIe and the CTL, they're compatible. So how can we do that? We call it extending the PCIe transportation. So actually today, when we use some like NIC cards, use adapters, we transfer the data from the one CPU to another CPU. We need to cross the whole flow. We need to have PCIe link, 30s to 30s, and then we have some PCIe to network translator with so-called DPU. And then we need to send the signal across some switches and then go back again. So why bother? Why we do not just bring it together? Why we just do not connect all the 30s together with the PCIe network? Then actually, a lot of people doing that right now, not just us. Then we divided it into two things. One's called pseudo bus. We use some RDMA with a remote direct memory access. We need some adapter to make the two processors can see each other's memory. They can see. Then called RDMA. Another part is called UMA. We actually share the same memory space, and then they can just read and write across the whole memory space. So the players in this area, of course, NVIDIA IB, as I said, is RDMA native. It's very good, and the performance is good, but it's very expensive. Google team, they are trying to lower the price, and Huawei, UB, Unified Bus, they're trying to do that as well. So, and of course, the Intel, Rocky. Then for the true bus, if we want to share the memory space without any adapter, we need to use the bus. The NVLink is one of them. NVLink to do the GPU to GPU. Actually, all the GPUs, they share the same GPU memory space. And in Fabrica, they use some AC advanced composable fabric compared with the CTL, and we use the PCIe. So what should we do? We have a lot of links, but what should we address? So questions we need to address in the next generation interconnections, I think there are 5 parts we need to consider. First one, we need a unified interface. So why? As I said, Intel and AMD, they have all ARM, they all have their own link to connect to CPUs. But can they all share the same controller with the same SerDes? Before the PCIe generation 5, it's very hard. But after PCIe generation 6, they all use PAM4 as the SerDes. So it should be easier. So I think currently the community or the industry, they are they have some some unified interface protocol right now. Another one that how can we reuse the functionality? Because we do not want to just connect the CPU to CPU. We want to connect the CPU to GPU and GPU to GPU. So can we just have some function reusability across all the new link, especially for the controller and the protocol? Of course, third, we need to compatible with the existing architecture. We do not want to change everything. We want to use the PCIe. We want to use the current PCIe to do the same thing. And then what kind of API export to the user space? How can the application to drive this new link with this protocol? So the last one, what is the key applications? When we have some change in the interconnections, what kind of applications we need to do to make it is more business feasible? Not just we just build up something state of art, but no people use that. So these are 5 aspects we need to think about this new technology. So our solution is very straightforward. So we just we usually have a SOM, use the SI6 in package. We just put the PCIe and the Ethernet together. We use the Ethernet to initialize the PCIe, and then we call it hybrid switching. So we use a hybrid switching. We can do both the port-based routing. This is, this is advantage of Ethernet. You can always do routing by the port-based. And also the PCIe switch is very good for the device tree addressing, actually memory space addressing. So as long as you have the memory space, memory address, you can also do read out and write out very fast. So we just put them together, and then we have a fabric ASIC. And also we have a software defined to define what is route. So, okay, I do not to talk about too much about this, but the interface right now we employ is PCIe and also Ethernet. In the future, we use a CTL to unify it, because the CTL, they will introduce the port-based routing in the CTL 3.0, and also they have the global memory. So this is the players right now in the data center I/O, especially in the bus side. As I said, the Google, they introduced the team. It's pretty good, but they need an adapter. Right now, the key point is how to lower the adapter's price. And NVLink is very good, very high performance. The only problem that they only, for NVIDIA only, and also for NVIDIA GPU only. They do not even do the NVLink for the CPU. They need a new link. It's called the NVLink C2C for the CPU. So they need some like more features. And then in Fabric, they introduced the mix of the PCIe and the Ethernet. Actually, in the we use the same thing as well. So, but the difference is with the PCIe, we do not use the CTL. CTL is too expensive currently. Yeah. So this is a summary about what we think about the interconnections. We see the application from the top. We divide it into two parts. One is for the cloud native, like TCP/IP, and another one for the HPC. And then for the protocol, we use the TCP/IP, and then RDMA verbs. And the fundamental, actually, you see they are the same. They're all like InfiniBand, Ethernet, also PCIe. So actually, it's all the foundations of all these applications, they come to merge because of the 30s evolution. But right now, the difference is between all the controllers and also protocols. So in the future, we want to say, hey, can we do something about the PCIe? And we call this part, we call the TCP/IP one is the PCIe net. We call the RDMA is the PCIe fabric. So this is our idea that for the next generation server design or like system design, we need to think about the multi-core CPU and the green efficiency. And then the last part is the connection. How can we build a more efficient connection to connect the multi-core and also the efficient core together? So we think that PCIe, CTL, and Ethernet will be the future. So in the Arduino 5, we just summarize the landscape about the connections from TCP/IP to the UCIe. Like we think about this, it's purely because of the distance. In the chiplet and the system impact, these are the small distance, maybe with like UCIe. But for the system on board and the cloud on board with the PCIe, of course, beyond that, with the TCP. So at the end, we just show some progress. We use this architecture to do the object storage and also the high-performance storage. So the architecture is very straightforward. Just we, consolidate this part, the PCI switch and the NIC, and also the Ethernet switch together with one chip. And then we connect everything into this chip. And for the HPC server, we choose the more powerful CPU. So with NAS CPU, but more PCIe ports, and the NAS switch ports, and for the application, which is the NVMe over Fabric, and also for the HPC. So Microsoft, we use like a low power SoC, and then we use more, and then the PCIe port normally is fewer, and then the switch port is more. Then this is for object storage, and also like cold data storage. And this is architecture that we mix the PCIe. The bottom part is the PCIe. The upper part is the Ethernet. So with the Ethernet to connect the two CPU, with the PCIe to connect to storage controller. Actually, this is the PCIe switch. So this is our, if people are interested in, we can discuss more in the booth tomorrow. So we can extend the PCIe. This is the first PCIe connected storage, completely use the PCIe net, and we can scale to 7 petabytes with a very low power consumption. We can lower each bay only, each hard drive bay is only 2.5 watts. This is about like 15 lower than traditional ones. And also we have another solution. It's coming next month to connect all the powerful Intel CPU together. We can reach like 20 million IOPS for the NVMe over Fabric, and also we can extend it. We can have like a 48 NVMe storage directly connect to the CPU. So for the network, we can up to about 1 terabyte per second. Of course, the SPDK and the DPDK ready for ultra low latency. So thank you. That's my sharing today.
Any questions?
Question I think I asked before. How are you going to play the DPU workload? And when are you going to migrate to CSL?
That's, okay, let's go back. Oh, sure. Actually, we discussed with Marvell and some other DP vendors about this. And that key point that how they define this interface. Today, most of the DPU, they just use the DPU as a CPU. They run all the applications in the CPU. And then they have like a light VM, like a hypervisor to communicate, use the PCIe. But it's not that mature yet. Some people just use like a Ethernet, like a internal Ethernet to do that. So we think in the future, CTL will solve the problem because CTL have some Ethernet routing feature in the protocol itself. So, but currently right now, I think people use the Ethernet or use the PCIe, just use like a driver to solve the problem. So, yeah.
Yeah, I think this is a key point, how you can bring this blueprint from mature state to the core state.
So our idea is that, okay, we want to make things easier. We just built up Ethernet between these two. Even they run based on the PCIe interface. But for the host, they see a virtual link. So that's why we want to make it more transferable to different systems. Then we do not need to log to like vendors. So for the DPU here, you run the management here, right? Then you have an interconnection to the host based on the Ethernet. So the only thing we need to maintain is the driver here. Other than that, people do not need to change anything in their application. That's our solution.
Yeah, thank you. I got the answer, but I hope this answer can be optimized into the open source mainstream solutions.
Yeah, we'll try. Yeah, we need some help.
At the beginning, you mentioned about your company, like 10 to 20 servers with like 2 switches. And are you saying this is kind of your typical user case? But in my imagination, or like I can't really think of a real user case like with like 10 to 20 servers switch from the traditional architecture to this new type of thing. I think it would like make sense in data centers, but I don't really, I can't really picture. So can you give me some example or like your user case?
Sure. Actually, we think about this for a long time. You know, in the beginning, we have some, we feel a little bit like how we can promote our technology with the marketing. We found that Amazon gave us a very good example. Amazon right now, they ship the post. Actually, it's integrated rack with all the servers. So they just give the customers an integrated rack with the servers, Amazon certified. And then they deploy the Amazon cloud, like edge cloud, to the customer. So our business, we want to have some partner. They can provide like a hybrid cloud, maybe with Alibaba, with Tencent Cloud, and then we provide the hardware. We provide like a hardware in the rack. We have everything inside. And then our partner, they only need to deploy like a storage or deploy the cloud. And then we have hybrid cloud. The customers do not need to care about what is the vendor for the hardware. They only interact with the cloud provider. That's what we are working on right now. So we work with some like a private cloud, like storage cloud company. We have the turnkey solution for the hardware, and then they build up the turnkey solution for the software. Then together, we lower the total TCO for the customer. Right now, we're doing this right now, yeah. we can see a change for this area dramatically because people do not need to, just like a GPU, people do not want to take care of the cluster right now. It's too complicated, yeah.
Yeah, I've got questions regarding the NVMe, the protocols you're using. So are you using the NVMe over TCP or using some other protocols?
That's a great question. Actually, we are working on that right now, but we have one progress. We built up a TCP on top of the PCIe fabric, and then we built up NVMe over the TCP on top of the PCIe fabric. Right now, we want to build up a NVMe over the fabric purely based on the PCIe fabric. We are working on that right now. Right now, it's working on 3 layers, so the performance is not that good. But if we can remove the TCP layer, the performance will be very good because of latency is really low in our case, yeah.
Okay, thank you.
Yeah, that's great. Yeah, we are working on that right now. Thanks, yeah.